All right, y'all. I'm not going to lie. We have reached the Everest of what I believe is AP Chem, and that is the equilibrium unit. Now, in my approach for AP Chemistry, I break equilibrium down into 4 separate units. So I break it down into general information about equilibrium, which is where we are right now. So this is going to cover this unit 8, all the very basics about what is equilibrium, how do we handle the math, that kind of stuff. Then I'm going to break it into solubility, acids and bases, and then buffers and neutralizations. And so this is kind of, like I said, the Everest. So if you think about this, we are at base camp right now, trying to acclimate ourselves to being on the mountain. And none of it in and of itself, I think, is extremely difficult. What happens is it's the challenging part of equilibrium is recognizing what to do when and when to apply each situation. So we're going to kind of spend a good chunk of time working on things so that we are very much prepared for looking at a problem and saying, hey, I know how to tackle this, or I at least recognize the words that are on this problem. If you can get that point, we should be at least moving in the right direction. So we're going to kind of start off equilibrium today very generally, and then we will wade more into the details as we get into units 9, 10, and 11. So this is just kind of the units, but if you think about it, we are close to the end, which is also very exciting. So I asked you before you watch this video to watch the TEDx video on equilibrium because I think it does a really good job of explaining reversible processes. And the heart of equilibrium is the idea that not all reactions are a one-way street. So this is a reaction that we've talked about before. This is not balanced by any means. This is just the combustion of methane with oxygen. And you know that once we light up methane, it goes and it turns immediately into CO2 and H2O, assuming that there aren't any side reactions that happens. But it is a one-way street. Once you light that up, there's not a lot of carbon dioxide and water turning back into oxygen and methane. It's a one-way street. So we call that an irreversible process. And I would say throughout most of chemistry, we focus on irreversible processes because honestly, they're easier. Stoichiometry applies here. I have this many grams, I'm going to get this much product, and my life is really, if you think about it, fairly easy if you like that kind of thing. When we get into reversible processes, though, what happens is things are not quite as cut and dry. So an example would be the production of ammonia. Ammonia is produced when I take nitrogen and get it together with hydrogen. Usually you have to heat it up quite a bit, and it turns into NH3. Now, that process is not a one-way street. In fact, it's kind of difficult to make that happen. And through chemical manipulation, I can make that stuff, but it's tricky. And what happens is when I start my process, the nitrogen and the hydrogen get together and they turn into this ammonia. But at the same time, then, as that's happening, we have the reverse process happening. And so they kind of go back and forth. Reactants turn to products, products turn to reactants, and it goes back and forth. And when we talk about reactions that are reversible, that process continues all the time. So it's perpetually changing, and they call it a dynamic situation because even though you maybe can't see it with your eyes, the process of reactant to product and product to reactant is always happening. So it's always changing. There's always stuff colliding. There's always stuff breaking apart, new stuff forming, and that process keeps going on. Whereas in an irreversible reaction, we just kind of go A to B and bada bing, bada boom, we're done. So what happens is the considerations in terms of math and stuff like this are a little more complicated because we have to take into account that persistent change that happens. Now, that being said, a reversible reaction reaches what appears to be a steady state when we hit this point called equilibrium. And so what equilibrium truly is it's when the rate of the forward reaction, so how fast we change from, and I'm sure this looks backwards, how fast I change from reactants to products is the same as I go from products to reactants. So the rate, how fast that is changing, hits a constant. And so what happens is it looks like the reaction has stopped. It looks like nothing is changing, but what's happening is the amount of stuff we have going one direction is equal to the amount of stuff changing in the other direction, so it looks like things are the same. When you reach equilibrium, there's a couple of things to keep in mind. Your system is going to be closed, which means that we're not pulling anything out or putting things, in. So when we talk about a system reaching equilibrium, it's kind of like its own closed little system. Like I said, both your forward and reverse reactions are taking place and the rate of change is equal. So the rate forward and backwards is identical. And here is the key with this. Equilibrium does not mean equal amounts of chemicals at that point. It's an equal exchange of chemicals, but not an equal amount. So just because I hit equilibrium does not mean that I need to have 50% of one chemical and 50% of my product chemical. Like, that is not how that works. It just means that I've reached a point where it looks like my reaction has stopped changing because I have the equal amounts going back and forth. We will be talking about how we identify what is more present in just 1 minute. Here is what I like to talk about for equilibrium. If you guys have ever shopped on Black Friday really early in the morning, or you've seen it even on the news, you see those people who are like, I'm going to get that TV, and they're super crazy. What I like to do is I like to think about equilibrium as a store that's open on Black Friday, and it has 2 floors. So it's got an escalator, which I personally find terrifying. And it's got one escalator that goes up and one escalator going down. So think about our reaction as reactants on the first floor and then products on the second floor. So if you think about it, when Black Friday starts, all the people start off on the first floor. So you've got all of your reactants as reactants, and we've got nothing going on. Now, get started, store opens at whatever time it happens to be, and then you get this big rush of people going up the escalator because let's say that, $10 big screen TV is hiding up on the second floor. So they always put those items up really far in the back corner, so you have to walk past all of those other things, so you grab more things as you buy. So let's say your TV is up on the second floor, and I got this whole crowd of people who are rushing up there. Now, the initial movement, if I start off with all reactants, is going to go heavily to the product side. And if this were an irreversible process, they would stay up on that floor and never be allowed to go back. If you think about how a reaction works or a store, not everybody wants that TV. So some people are going to stay milling around looking at sneakers or whatever on the first floor. But the bulk of our people, if they're coming for that deal, are going to go up to the top. Okay. Now, you get up to the top, you either grab your TV or realize they never had enough for your entire group of people who were there. And what happens is, as time progresses, some people will start to go down. And so what you'll see is a sort of a traffic flow where some people are going up the escalator, some people are going down. And this is what a reversible reaction is. So I have some reactants that are turning into products and some products that are turning back down into reactants. So that's kind of how I envision this. So equilibrium is not at this point here. If you think about this, I've got 3 reactants and I've got 3 products. I am not at equilibrium at this point. I reach equilibrium when I have the same number of particles on the escalator. So if you think about it, if I go back one, equal amounts here, but I've got 3 particles going down and 1 particle going up. So I'm not at equilibrium. I am at equilibrium at this point because I have 3 people going up and 3 people going down. So what happens is it looks like the number of people at the top of my store and the bottom of my store is identical, because what will happen is I will get 3 going up and 3 going down. And so that number is going to be unchanged. And that is equilibrium. So equilibrium is when that same amount of chemical is passing back and forth from both sides. Okay, so when we talk about equilibrium, like I said, the math on this is not quite as straightforward as it would be with stoichiometry. So what we do is we write something called an equilibrium expression to start to deal with that. And an equilibrium expression deals with chemicals that are changing in concentration throughout our process. And in the case of most of these reactions, the only thing that's going to be changing are going to be things that are aqueous solutions and things that are gases. And that's because if you think about their amount per liter, it is going to change as the reaction progresses. Your quantity of, let's say you have a solid or a pure liquid in there, will also change, but the concentration of it is always going to be 100% that pure liquid. So what we do is when we tackle this math, write something called an equilibrium expression. And an equilibrium expression is, like I said, the first step to getting to dealing with the math for these reactions. And the way I write an equilibrium expression is I write a ratio of products over reactants. So always keep it in your mind, products over reactants. It's not dissimilar to thinking about products minus reactants when we talk about our enthalpy changes or things like that. And what happens is in our equilibrium expression, in that ratio, you take each substance that's either aqueous or gas, and then you put them into these little brackets. Now, these brackets represent molarity. If we were talking about a gas, we could either write it as a molarity, because sometimes they do report gases as molarity, or you could put it in as a pressure. Now, pressures would be like atmospheres, torr, those kinds of things. And then what happens is the coefficient that's in front becomes the power. Now, this is not the same thing as a rate law. So remember, we talked about how those coefficients don't become the powers. In an equilibrium expression, they do. So if this is a 2, this becomes a squared, and so on. And then you do that for all of your reactants on the denominator part of this expression. So like I said, though, you're going to leave out pure solids and you're going to leave out pure liquids. So if you see like solid iron, that's not in there. Liquid water, not in there. So one of our first examples with equilibrium expressions is going to be talking about a reaction that we call the autoionization of water. Water on its own actually kind of breaks up a little bit into H plus and OH minus. And so we're going to take a look at what that reaction does as far as its equilibrium. Now, it doesn't happen a ton. It doesn't break apart a ton. But when we look at its equilibrium expression, which is its KEQ right here, so KEQ would equal the concentration of H plus times the concentration of OH minus. Now you might say to yourself, where is the H2O here? If you think about what the definition is for this is not going to cooperate, is it? Our expression, it is a ratio of products over reactants. So if you think about this, I've got H2O aqueous and H2O and OH minus. I'm sorry, let me back up again. I have H plus aqueous and OH minus aqueous, and those go into my top part of my equilibrium expression, and they have superscripts of 1 and 1 because of the coefficients here. H2O gets left out in this case because it's a pure liquid. So its concentration when it's made is always going to be 100% pure liquid, so we don't include it in the equilibrium expression. Had this been a reversed reaction where I had H2O as my product, I would have a 1 in my numerator, and then H plus and OH minus would be in the denominator. In this case, the K value for this reaction is 1 times 10 to the negative 14th when it's 25 degrees Celsius. K values are temperature sensitive, just like lots of other things are. And in this case, the K value, because it is very small, means that it's reactant favored. What you actually see is that Ks that are less than 1 are going to be reactant favored at equilibrium. So what that means is that at the end, when all this settles down and I get to a point where my rates are equal going back and forth, technically not the end, but you know what I mean, I'm going to have a heck of a lot more product here and not a lot of reactant. And it's because these numbers are very tiny and this amount is very, very large. The bigger your negative exponent gets, the more reactant you have. So in this case, since it's to the negative 14th, it means I have basically very little to none of my ions present at equilibrium. It's not a lot. Interestingly, this also ties together with Gibbs free energy. We will be doing some math with this, but in this case, because it's reactant favored, it means that our Gibbs free energy is positive. All right, another one is going to be this reaction here where we're making HI from H2 and I2. So in this case, our equilibrium expression is going to be the concentration of HI squared because of that coefficient of 2 divided by the concentration of H2 times the concentration of I2, and those are both to the first power. Now, if this were a pressure instead of a molarity given to you, you would put pressure of HI, pressure of H2, and pressure of I2. And that would actually be called a KP. And we will dig more into that in a little while. In this case, if you see our K value, this is a big K. And so this big K that's greater than 1 means that our reaction is product favored. So at equilibrium, I'm going to have a larger amount or a larger concentration of HI than I would H2 and I2. And so I get a number that's greater than 1. And the greater that this reaction K value is, the more product favored it's going to be. So if you think about Gibbs free energy, it's more negative then. Reactions that have a K value of 1 are kind of a blend of reactant and product favorites. They're kind of neither, and they have a Gibbs free energy actually of 0. If you have a K that's mega, like we're talking to the 14th power, to the 15th, like huge K values, even this one's honestly pretty big. What that means is that you have basically almost all product and not a lot of reactant present at equilibrium. Now, they might ask you to graph this. And I'm going to show you guys 2 different graphs for this particular reaction. There's some good parts of the graphs and there's some not great parts of the graph. So this first one here, if you think about what it represents, if we look at the shape, I'm starting with my reactants and their concentration is dropping, and I have products showing up and their concentration is going up. Now, if you think about what's not good about this graph, these particular shapes here do not represent the rates of change particularly well with regards to the coefficients. So if you think about the rate of change, this drop in concentration should be at about half the rate as the HI shows up because this has a coefficient of 2 and these have a coefficient of 1. However, in an equilibrium graph, what we do see is we see a plateau. That plateau is the point where we reach equilibrium, where we have our concentrations remaining unchanged. And this is the part that I do like about this. So in this case, the concentration of HI is greater than the concentration of the reactants, which lets me know that my KEQ is going to be greater than 1, or it's going to be product favored. I also think that this graph is really interesting because one of the things that's true about equilibrium is that you can get to equilibrium whether you start with all reactants, all products, or a combination of the 2. The system naturally settles out into its equilibrium point. And this graph, what it shows is that I have some HI that turns into my products. Again, the ratio is not great. But what is important in this one is that we do reach that plateau and that my ratio of HI is still greater in concentration than the H2 and the I2, which still makes me know that this is a product favored process. All right, we're going to take a look at this graph. I want to see what you guys can tell me about this reaction. So we're going to look at this, and there are, I guess, 2 things I want you to tell me. 1, does this graph, I should say 3 things. 1, does this graph make sense with the balanced equation? 2, do I start off with all reactants and no products? No products and all products and no reactants, or a combination of the 2? And then do I end up product favored or reactant favored? And what does that tell me about the K? So think about it first. We'll talk about this through. Does this graph make sense with the shape? A plus 2B turns into 2C. If you think about what we talked about in kinetics previously, A is dropping in concentration at half the rate of B, which means that coefficients are 1 and 2. Concentration of C is going up at the same rate as B is going down. So this graph makes sense, that's good, unlike the other one. All right, next thing we want to look at, concentration of A and B are going down as C is going up. So this tells me in this case that I started off with all reactant and I am making some product here. Because of the final resting place of my my product C at the top here, since it is higher in concentration than both my A and B, it lets me know that my reaction is product favored, and that means that my K value is going to be greater than 1. So we will kind of dig into this a little bit more in class and then get into it with your homework. If you have any questions, please make sure you get them clarified. Otherwise, good luck.